So I'll continue with my series of basic organic chemistry, where I'll be taking today lecture 14th. You remember in the previous lecture 13, I had taught about different types of organic reaction, in which the primary first thing was nucleophilic substitution reaction, in which there are two types of nucleophilic substitution reaction, that is SN reaction. In that two types are SN1 and SN2. Then amongst that I had taught you SN2 reaction, including the stereochemistry of the SN2 reaction. How does that SN2 reaction go? Means methyl radical is first preferred over primary and then secondary and then tertiary. Methyl halide is preferred first over, methyl is preferred over primary halide over secondary halide, which is preferred over tertiary halide. Right? So primary comes first, primary is more than, secondary is more than tertiary. Right? Now, even I have taught you about leaving group, the strength of leaving group, how lower the basicity, stronger than this leaving group capacity. The lower the basicity of a particular group, more it is a better leaving group. Lower the basicity and better the leaving group. Similarly, good the leaving group, better the leaving group, greater is the reactivity. Greater is the reactivity. Better the leaving group, better good the leaving group, better is the reactivity of a particular reaction. So these things I had done in lecture 13. So now today in lecture 14, as in lecture 13 we had done about SN2 reaction, right? Now in lecture 13 we will do with SN1 reaction. Now what do you mean by SN1 reaction? What type of what exactly is SN1? There are how many types of reactions there, substitution reactions are there? We'll do it in this lecture. Fine. So I will start the lecture, but prior to starting I will just request you to just, if you like my content, you can just go through the content thoroughly and share it with your like-minded people and who really like organic chemistry and the mechanisms. I'll be very helpful to you if you let as many students see it, and so that they can learn a lot. I request you to please do share, like and subscribe my channel. And if you are looking me at Facebook, then do follow me. And if in YouTube, then obviously you do like and subscribe. And please also write the comments. From that comments, I'll be able to understand what is the scenario. And even you can email me or WhatsApp me. Everything I've given you in the details I've given in the description box. Right? So I'll start with the lecture. Now. Primary, what do you mean by SN1 reaction? SN1 is nothing else but unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reaction. Yeah. Now, so unimolecular means in SN2 it was a bimolecular. SN2 means bimolecular and SN1 means unimolecular. And as I told you in SN2 reaction, there the rate of the reaction depends upon both the alkyl halide as well as the nucleophile, which is going to attack the alkyl halide, right? But in this case, in SN1 reaction, what happens? It's a, suppose this is the alkyl halide, which is attacked by a OH minus, which is a nucleophile, right? So here what happens? Plus X minus. I hope you are able to hear me and you can understand now. Now basically this is a two-step reaction. It's a two-step reaction. Now what do you mean, what is the first step? First step is nothing else but formation of carbocation. Carbocation means positively charged carbon atom. Take for instance R, C, R, R, and then this is the X, right? Initially what will happen? The X will part off the first step. This will be the first step, which is primarily also the RDS. as you know, rate determining step, or as I've told you, it is the slowest step in a particular reaction is known as the rate determining step, right? It's not properly visible. Yeah. Yeah. R, C, R, R, and then plus X minus. So the first step happens to be the formation of a carbocation. Formation of a carbocation, right? And this is a reaction intermediate. This is a reaction intermediate. R, you have to be more precise, R, R dash, R double dash. Means either one is methyl, ethyl, propyl, whatever. 3 means either 3, all the 3 are different, fine. Or the 3 can be same, nothing else. But you can say primarily, what is this? This is nothing else but a tertiary carbon atom. Tertiary carbon atom. I can say it's a tertiary halide. It's a tertiary halide. Right? So there is a first step is the formation of carbocation. Now what happens to the second step? Second step is nothing else, it's a fast step. It's a very fast step. Fine. In this what happens? The carbocation which is there, this is attacked by a nucleophile. Now what happens? The nucleophile has two possible position by which it can attack. Either it can attack from the front side or from the back side. That means either it can attack from here or it can attack from here. So this attack, take for example A and this is B. So if it attacks from the frontal position, that is A, then the product will be R double dash dash nucleophile. And if it is, this is, take for example by path A, by method A, when it attacks on the frontal part, frontal position. And take for instance, this is a nucleophile, and then this R, this is R, and this is R, means R, R double dash, R triple dash, right? So this is that is a backward attack, I can say. Backward. This is the frontal attack and this is the backward attack. That means two possible, you can say isomers it's obtained. Isomers. Because what do you mean by isomers? Same molecular formula but different structural formula. Here the molecular formula will be the same. In this molecular formula will be the same, but the structure has changed. And even you can say even the stereochemistry of the molecule has changed. From one it is on the frontal side, from one other is the backward side. Now obviously if it is on the position of the bonds, everything are going to change, right? So I can say two isomers have been formed. Now if I show you what is the stereochemistry. Stereochemistry. Suppose, take for example, this is the solid bond. Take for example, this is the first step will be this will be the positive charge. This is the carbocation, which is the redetermining step. Fine. This is the carbocation. Now what happens in the second step? This is the first step. Now in the second step what happens? There is an attack of a nucleophile. Nucleophile can attack, either it can attack from here or it will attack from here. If it attacks from the frontal part, then it will be as such. The bonds, the position of the bonds are not going to change. The position of the bonds are not going to change. But when it attacks from the backward side, obviously when it attacks from the backward side, the position changes, right? this changes and comes here. So I can say this is nothing else but retention of configuration. Retention matlab as it is. So as the substrate, similarly is the product. Though it is retention, as I've explained in the previous lecture, this is nothing else but inversion of configuration. Inversion means totally opposite. So in retention, and this is 50% and this is 50%. That means I can say 50% of retention and inversion of flow. That means I can say there is a formation of a racemic mixture. Racemic mixture. That means the two isomers are formed. That means I can say enantiomers are formed. Enantiomer, because what are enantiomers? Non-superimposable mirror image. Non-superimposable. Although these two are mirror image, seems to be mirror. When I put a mirror in front of them, then obviously it is a non-superimposable. This structure and this structure are not going to overlap on each other. So they are non-superimposable mirror image. So they are known as isomer. So I can say in SN1 reaction, you can say nothing else but it's a two-step reaction first of all. Then it is via formation of carbocation. Then there is a enantiomer formation, right? That is racemic mixture. Racemic mixture means 50-50. Because of 50-50 mixture forms, that means a racemic mixture is formed, right? Now, as we know that reactivity of any reaction is directly proportional to the stability of the reaction intermediate. Here the reaction intermediate happens to be a carbocation, right? This is the reaction intermediate. The stability, more the stable carbocation, more is the reactivity. Now, carbocation, we know we know what is the stability of carbocation. Stability is for carbocation. We can say tertiary is more stable than secondary is more. Tertiary is more stable than secondary is more stable than primary. Fine. Obviously, if tertiary carbocation is more stable, that means understood tertiary halide has to be first, because tertiary halide only will give me tertiary carbocation and primary. So this will be the preference in scenario of SN1 reaction. And obviously tertiary, secondary, primary, and then the least will be methyl. As in case of SN2, first was methyl, then primary, then secondary, and then tertiary. But here it is the opposite way now, right? Because now, as we have seen that in carbocation which is a positively charged species, in which R, alkyl group, which is an electron donating group, more the electron is donated on the carbocation carbon atom, more is the stability. So obviously tertiary will give me more stable. Now, yeah. Now this reaction is done in what? It is done in polar protic solvent. No. What do you mean by polar protic solvent? Polar protic solvent, like example as water, or you can say methanol, acetone. Everything I have taught you in the previous lectures. Methanol, polar. Polar means two poles are generated. Two poles are generated, and protic matlab it should contain some proton. It should contain a proton. Why? Now, why a polar protic solvent is preferred? Because the polar protic solvent will form a type of cage. It will form a cage. It will form a cage on the carbocation. A polar protic solvent will form a cage on the carbocation, just leading to the stability of the carbocation. So that means the stability of the carbocation is more due to the polar protic solvent only, right? It stabilizes the work. So it's very important point that polar protic solvent is preferred. Polar protic solvent is preferred, right? As we know, in the scenario of SN2 reaction, there polar aprotic solvent is required. Why? A polar aprotic solvent is required in scenario of SN2 reaction, right? Because what happens, SN2 reaction, if it is a polar, take for instance, if you take even a polar protic solvent in SN2 reaction. Now we know SN2 reaction, nucleophile is there. There is only one type of attack. That is it will attack from the back side of the halide, right? And it will displace the leaving group. Now, suppose if I add a polar protic solvent which will contain a proton, so obviously it's quite possible that it can mask the nucleophile. And if it masks the nucleophile, obviously then the reaction is hindered. Then the reaction does not take place easily. So a polar protic solvent is a must. As we know, in the previous lecture I have told you, polar aprotic solvent is a must in SN2, but in SN1 strictly polar protic solvent only, because prior to addition of a nucleophile we are using this polar protic solvent, because prior to this addition of the nucleophile, the polar protic solvent will stabilize the carbocation. More the stable of the carbocation, then easily the reaction will happen, right? Now what will be the stereochemistry? Stereochemistry means arrangement of atoms in space. Stereochemistry. Now what do you mean by stereochemistry? As you know, now here the nucleophile can attack, as I have told you, the nucleophile will attack on the carbocation from both, from the frontal part or from the back side, just leading to the formation of 50-50 racemic mixture, that is enantiomers, right? Now if I want to do a simple comparison between SN2 reaction and SN1 reaction, I will say SN1 reaction is a one-step reaction. This is a two-step reaction. There is no transition state. There is transition state involved. That is carbocation. Nothing else. It's a transition state. The formation of carbocation, which is a rate determining step. And here, no doubt, the attack of the nucleophile, that itself is a rate determining step. Fine. Now, in SN2, the methyl is more than primary carbon, then that secondary carbon, and then tertiary carbon atom. Scenario in this, tertiary is more than secondary halide, is more than primary halide, is more than methyl. Now, in SN2, a strong nucleophile is preferred. A very strong nucleophile is preferred, because now the strong nucleophile is preferred because it has to kick off the leaving group. In SN2 reaction, it has to kick off the leaving group. Then it can only happen because if it is very strong. If it is a very strong nucleophile, then it can easily remove the leaving group. And not only strong nucleophile, but also a good leaving group. The leaving group also has to be good. Then only, a strong nucleophile. Suppose if a strong, very weak leaving group is there. A very weak leaving group, but it is not ready to do part of. A good leaving group means it will easily. And a strong nucleophile. So a strong nucleophile can easily replace a good nucleophile. But if I take a weak leaving group or a very strong leaving group, means a weak leaving group, means who does not want to leave, obviously then the strength of nucleophile has to be very, very strong. The reaction itself will not take place, right? So both the scenarios have to be, it should be a strong nucleophile, it has to be a very strong nucleophile, and it has to be a good leaving group. Now in this scenario, here the nucleophile can be normal, no need of any strong nucleophile. A normal nucleophile will do, or a weak nucleophile also will do, because it has to go with a frontal attack. Frontal attack means easily it can happen. But in this scenario also the leaving group has to be very good. It has to be a good leaving group. Because a good leaving group only will easily form carbocation. If the leaving group is bad, then the formation of carbocation becomes difficult. Right. Now, we will see some different types of types of nucleophilic substitution reaction, right, which are given by first. I will just few examples I will take. Benzyl carbon. You know what is benzyl carbon? Take for instance, this is benzene ring, CH2 halide. This is the benzyl carbon atom. This is the benzyl carbon atom. Suppose to this electron donating group like OCH3. OCH3, take for instance, which is an electron donating group. The electron donating group is attached, fine, then it will donate electron towards it. Then what will happen? Then it will get a partial negative charge will come out here, right? And this is already negatively charged, then obviously there will be a repulsion. So there will be easy formation of a carbocation. There will be easy formation of a carbocation. That means, can I say a benzyl group in this, if a electron donating group is attached, then it will give a SN1 reaction. SN1 reaction. Similarly, if a NO2 group is attached, that means I can say NO2. NO2 is nothing else but electron withdrawing group. It will pull all the electron towards it. Then this becomes positively charged, partial positive charge, and here obviously negative. Then obviously it is not going to leave the bromine as a good leaving group. So here the SN2 reaction has to take place because there is no chance of formation of any carbocation. So here the what happened? NO2. Then here the problem is NO2 and obviously here CH2 will take place, right? So whatever, if I react it with a nucleophile, then CH2 with a nucleophile will come into picture. Similarly will be the here. If I attack with some nucleophile, then obviously it will be some CH2 with a nucleophile. Product both are same, but depends upon the electron withdrawing and electron donating and electron withdrawing group. If electron withdrawing, then it will give SN1 SN2 reaction, and if it is electron donating, then it will give me a SN1 reaction. Fine. No. One more example we will take. Take for example alkyl halides. There are many different examples are there. Take for example RX. If I take some water or NaOH, right, then the product will generally form ROH. Suppose if I take OR dash, then it will form ROR dash, right? Then if I take sodium cyanide NaCN, then obviously it will form CN. But if I take AgCN, then it will form RNC, isocyanide, right? RNC it will form isocyanide. Now suppose if I take a sodium salt of ester, CONA, then obviously ROC double bond R dash, suppose R, this is R dash, right? Now similarly if HNO2 is there, then NO2 comes into picture, O dash and double bond O. This because NO2 is a ambident nucleophile. Similarly CN is also an ambident nucleophile, right? But just make it a point that AgCN will always give isocyanide and NaCN or KCN, anything. KCN or NaCN will always give cyanide, CN. This will give NC, right? Both are ambident nucleophile, but depending upon the attachment to the metal, right? Sodium is a very strong, is a strong metal then as compared to silver. It's a stronger metal as compared to silver. So a stronger metal CN gives a cyanide, where the weaker metal CN gives a isocyanide. Similarly AgNO2. AgNO2 obviously it gives a ONO which is known as nitrito. Nitrito plus it will give me another R N double bond O single bond O. Okay? This happens to be a major and this is a minor. So nitrito is minor and this is major. Fine. This is another one. Sorry. Now then we will do about some a bit example. Alcohol. Now what do you mean by alcohols? What happens generally? They don't give nucleophilic substitution reaction with halides. Alcohols don't give generally. Means normally they don't give with halides. Why? Because what happens? A halide what happens is a weak base. Halides are weak base and weak bases cannot replace, and OH is a strong base. OH is strongly basic and halides are weakly basic. And a weakly basic acid, a weakly basic group halide cannot replace a OH. That means suppose if ROH is there and if I treat it with a X nucleophile, then there will be no reaction. There is no chance that it will form RX. Will not form RX because X is a weak nucleophile. It's very weakly basic. Therefore it can't replace OH. Fine. Now, so for that, if for that scenario if I want to do it, then first what we'll have to do, RH which is there, this I will have to first probe, because OH is a very bad leaving group. OH is a bad leaving group, because if for any group to act as a good leaving group or bad leaving group, as I have told you, weaker the basicity, better the leaving group. Weaker the basicity, that means I can say basicity is inversely proportional to the leaving power, right? The leaving power is obviously inversely proportional to the basicity. OH is a strong base, therefore it is a bad leaving group. But halide, which is weakly basic, so it is a good leaving group, right? Now suppose if I want to, that means first I will have to convert OH, which is a bad leaving group, into a good leaving group. For that scenario, what happens? I will have to treat it some halide, hydrogen halide. Take for example HX, hydrogen halide, like whatever, HI, HF, HCl, whatsoever. So what will happen? This O will get protonated, so it will form ROH dash H. This will become plus and plus X minus. Now this OH, this has become a very good leaving group. Now easily a halide will come. Now this has become a very good leaving group. Now easily a halide can come and then it can attack here and this will have to go here. Fine. Now, so ROH will never give RX under neutral condition. It will never give. First, that because X is a weak base and OH is a strong base. A weak base cannot replace a strong base. Fine. So first we'll have to convert OH into a good leaving group. For that scenario, we'll have to treat it with some HCl, some acid, so that the OH gets protonated and it will become OH twice. Once it becomes OH twice, then what happens? Then it will become OH twice and we easily nucleophile can attack on the R and RX will be obtained. Fine. I hope you might have understood till now. So if I want to see take for example, therefore I can say HI, which is that acidity is more than HBr, more than HCl. You can say this HI is a good acid, a very strong acid to be more precise. Good acid means a strong acid. It's a very strong acid because HI, if I say HI is a strong acid, that means it can easily part off as H plus and I minus, right? This is acidic, but this is a conjugate base. And if this is a strong acid, then the conjugate base has to be very weak. Conjugate base has to be very weak. So that is why I will become, I can say I nucleophile will be a good nucleophile. Up now will be a good leaving group. I will become automatically a good leaving group. Fine. So HI is a better leaving group. HI is a better, very strong acid as compared to HBr, as compared to HCl, and as compared to HF. You can say this is very important. Make a point on it. The acidity pattern, HI is more than HBr is more than in your school days you might have read, in the laboratory you might have seen HCl. That does not mean HCl is a very strong acid. No, HI is a stronger acid as compared to HBr, then as compared to HCl and compared to HF, right? In that halogen series, you can see. Now we will see the last one more thing. We will see ethers. Now the leaving power, you can say the leaving power of ethers, that means the OR section. Ethers means ROR, right? That means this is ether. The leaving power OR is equivalent to OH. That means OR is equivalent to OH. Means the leaving power capacity, of OH and OR are same. If OH is a very bad leaving group, obviously the OR is also a very bad leaving group, right? So the same scenario, since ether will not undergo nucleophilic substitution reaction. It will not show. See, if I am saying not show, that does not mean ki it will not show. It will show, if at all it shows, then it will show in a very drastic condition. Right? But generally it will not show nucleophilic substitution reaction. So you can say it is unreactive. Generally ethers are unreactive towards the SN reactions. Now, if I want to, same way, in the same scenario, since OH I have to convert it into a good leaving group prior to treating with a nucleophile. Similarly with OR will also be the same thing. ROR dash, suppose if I take this, I have to treat it with some acid. Then this lone pair of electron, this will attack on this, and this will become an ROR, and this is H. Now this part becomes a good leaving group. This is when attacked with a nucleophile, then it can easily attack here, and this will go here. Right? So OH and ether, they are of the same category because both are very bad leaving group. They will not. So they have to be first acidified and then only treated with a nucleophile. Obviously. Now we have seen these things. Now we will see another topic: the reactivity of acids and acid derivative. Acid in the sense COOH. Derivative means, take for example C double bond OR. Ester is an acid derivative, right? Ester. So acid or acid derivative. So you can say in both the scenarios, C double bond O. What do you mean by this? This is C double bond O is nothing else but acyl group, ACYL, acyl group, right? So I can also say reactivity of acyl derivatives. Now, the reactivity of acyl derivative basically depends upon the leaving group. Or the leaving power. This depends on first the leaving power of the leaving group. So how easily it leaves the substrate or the reactant. Now, as I have told you, leaving group is inversely proportional to 1 upon basicity. This is very important. Very, very important. Weaker the base, best the leaving group. Right? So I will say basicity in a decreasing order. Take for example. In decreasing order. H2 minus, O minus, then this is Cl. That means I can say this is the least basic and this is strongly basic. So strong and this is the least basic. If least basic, obviously then if it is least basic, the leaving power also is accordingly. The least basic will be a very good leaving group, so I can say the leaving power will be opposite, nothing else. Cl minus will be more than R, C double bond O, O minus will be more than OR, will be more than OH, will be more than NH2. The opposite of basicity, this part, the opposite of this will be this. Because weaker the base, better the leaving power. Weaker the base, better the leaving power. Right? No. This is very important, make a note of it. Weaker the base, better the leaving power. Cl was the weaker base, so Cl is a very good leaving power. Similarly will be the case of reactivity. If better the leaving power, obviously there, as I have told you initially, the leaving power also has to increase. So the reactivity of, you can say, of the acyl derivative in the decreasing order. I will say, take for instance R, C double bond O, Cl will be more than R, C double bond O, C double bond O, R. That means anhydride, which will be more than ester, fine, which will be more than acid, which will be more than R, amide. CONH2 means amide. This is another very important. The reactivity of RCOCl will be more as compared to anhydride, as compared to, which will be more as compared to ester, and that will be more as compared to acid, and right, because Cl is a better leaving group. So better leaving group, so any substrate having this RCOCl will be a better, will have a greater reactivity, because Cl is a very good leaving group. So the reactivity of RCOL will be much better as compared to the other scenario. Fine. So make it the point. Make these three, note of these three things. So 1, 2, 3, and very important. This is the important formula. If you remember this, then you can easily say what is the reactivity pattern, what is the reactivity, which group is more reactive. Because if you when you give this for exams, irrespective whether it is board exam, any board exam, or JE or anything, or IIT or anybody, there you are about to get at least one question or two where you will have to judge the reactivity pattern of that particular thing. So in that scenario, you will have to see if what type of leaving group is attached. And also, if you are unable to find the leaving group, then what type of basicity of that particular this is attached, right? So they all are interrelated. Basicity is interrelated to leaving group, and leaving group is interrelated to reactivity. So just couple all the three, and then you will be able to show the reactivity pattern. Fine. Now we have finished with aliphatic substitution reaction. Now the another type of substitution reaction. In aliphatic substitution reaction, we have seen a nucleophile, aliphatic nucleophilic substitution reaction. What happens? A nucleophile attacks a substrate, and in which it substitutes the leaving group. A nucleophile attacking in aliphatic in a nucleophilic substitution reaction, a nucleophile attacks. But there is another one, aromatic nucleophilic substitution reaction, or we can say ARSN, aromatic nucleophilic substitution reaction. In this, what happens? In this, it's the same scenario. A nucleophile will attack. nucleophile attacks, but in this case it will attack a aromatic ring. It will attack a aromatic ring, nothing else. In previously I have shown you in SN1 and SN2 it attacks a normal aliphatic compound, right? But in this scenario it directly attacks the aromatic ring. That means the benzene ring, aromatic ring. Because what happens, unlike the aliphatic compounds, suppose if a aliphatic compound has a nucleophile, right? And same aromatic compound is there, which also has the same nucleophile which the aliphatic is having. Suppose if aliphatic compound is having a nucleophile A, and the aromatic compound is also having the same nucleophile A, right? Now the reactivity of, or you can say the nature of that particular nucleophile on aliphatic substance, on an aliphatic substrate will be different as compared to the aromatic compound. But now what happens? The nucleophile does not undergo, now in case of aromatic scenario, the nucleophile does not undergo nucleophilic substitution reaction under ordinary condition. I'll give you an example. Take for example, this is chlorine, right? Chlorine is a living group, fine. Now, what happens if there is a RX? Take for example RCl. Now easily a nucleophile will come and this he will attack and this will go, fine. Now that was the scenario in aliphatic compounds in straight chain. But when it comes to ring, here the Cl was minus I. It shows minus I effect. Chlorine shows minus I effect in aliphatic. Minus I means minus inductive effect. Minus inductive effect means pulling electron towards itself. Now I think so. Now you're well versed with these things. Now, when the same nucleophile Cl is attached to an aromatic ring, here the nature changes. Here the nucleophile nature changes. Now here it becomes a plus R group. Plus R group means plus, the different, we have seen the electron movement. It becomes a plus resonance effect. It gives a plus resonance. Plus resonance effect means the lone pair of electrons are donated. Fine. That means there is a partial double bond always between carbon, between the carbon atom, aromatic carbon atom and the chlorine. So due to the presence of this partial double bond characteristics through the benzene, the leaving group is very firmly attached to the aromatic ring. Due to this formation of this partial double bond, this double bond inhibits the breaking of this bond, and therefore the leaving group capacity also decreases. As the leaving group capacity decreases, understood, obviously their nucleophile will be very difficult to attack, because the leaving group will not leave, chlorine will not leave, right? So what is the scenario? Suppose now I can say a minus R group will obviously take for example, this was a plus R group, it was donating plus R group. That means I can say a plus R group will create difficulties in aromatic nucleophilic substitution reaction. Plus R group will create difficulty in aromatic substitution, because the reaction will happen, decrease, the reactivity will decrease. But if similarly if I say if there is a minus R group means electron pulling, like NO2, right? Like NO2 or CN, NO2, CN are there, then obviously they will ease the aromatic nucleophilic substitution reaction. So plus R is going to create difficulty, and while minus R is going to act not only ease the back, means can I say this will act as an activating group for this, because it will create a partial positive character on the benzene ring. The minus R group will create a partial positive environment on the benzene ring, and due to which the nucleophile can easily attack on the benzene ring. Now I can say what are the different activating groups for ARSN. This is very important. ARSN. Now take for example this, just make a note of it, NH3 plus, then NO2, then CF3, then I can say CN, then SO3H, then you can say CHO. This is then C double bond O, ketone, then this will be COOH, right? Then this will be then amide, CONH2, then F, Cl, Br and I. So the minus I, this is the minus I groups, right? So activating groups, to be more precise. So pulling away of the electron from the aromatic ring. So NH3 plus will easily pull off. Then NO2. Similarly, when I go to the halides, where the electron pulling capacity decreases considerably. On the contrary, they donate the electrons, right? They have more act towards plus R group characteristics, right? So this is it's a very important, this, make a note of it now. Right? So this is nothing else but diazonium salt. ArN2Cl(X) the ArN2. Now what happens? This will undergo several reactions. It will undergo. The first type of reaction, take for example, if I take Cu2O in C, that means Cu plus 2 and water. This will give a number of reactions. It will go. So this becomes the backbone of many of the products to be formed. Diazonium salt becomes the backbone for many of the products. Take for example phenol. Formation can happen even via diazonium salt, right? Similarly, I will say CuX in presence of HX. Your X obviously can be Cl, Bri, anything. Then it will form an aryl halide. Similarly, if I take Ki, it will give Ari. Sorry, this X will be Cl, Br and can say Cn. Cu, Cn, ON, HCN it can be, whatever. Okay? But Ki is specifically for aromatic iodide. For aromatic chloride and bromide, we are using CuX. But when you have to form aromatic iodide, then Ki is the precise and the specific reagent which has to be used. I have told Cl, Br and I. Now in scenario of fluorine, again the scenario changes. HF and can say borane, BH3. Right, this on NaNO2 and Cu plus 2. Cu plus, and it will give ARF. Another also HBF4 also is there. There are many things. Now, suppose now H3PO2. In H3PO2 in water. Then it will give sorry, not H there, not this, just sodium azide NaN3 in water. It will give me aromatic azide N plus N2. Now then this on treatment with, you can say benzene C6H5 in formation of a sodium salt ester, sodium acetate CH3CONa, sodium acetate and water. Then it will give me AR which is attached to any other C6H5. That means I can say diphenyl type of compound is formed. Diphenyl. So you can see a diazonium salt can give so many types of reaction. Many more are there, but I have taken just a few examples. Why? Because arene diazonium salt. This is known as arene diazonium salt. By the way, arene diazonium salt. Arene diazonium salt or diazonium salt, you can say. No, because arene diazonium salt, what happens? Take for example, I will take to be more precise, I will take CH3O. And then it can undergo easily, it will undergo this. Fine? No. What happens? Sorry, this will become a plus charge because this is going. This particular group leaves. So it will become a carbocation. Now when as it becomes carbocation, fine. So you can say carbocation. So it is so a resonance is there. Always there is a formation of a resonance in this scenario. Therefore, it is more stable. Although stability is under a very cold condition only, at 0 to 5 degree only is the stability. At room temperature, the stability decreases. So it is more dependent on this. Now, another thing, as now we have just now we saw ArSN1. You can say this was ArSN1. ArSN1. Carbocation is formed in every case scenario SN1. Now we will see ArSN2. And this is basically speaking, this is the most common aromatic nucleophilic substitution reaction. This is very, very common. Now, and it basically depends upon the reactivity. Common and depends on first. No doubt, depends upon the reactivity of. It depends upon the reactivity, and the reactivity in turn depends upon the leaving group power. Right? So better the leaving group, better the reactivity. As I have told you previously just now, better the leaving group, better the reactivity. Bad the leaving group, the reactivity decreases considerably. That means I can say that reactivity is also directly proportional to minus R effect. Minus R matlab electron pulling, minus R effect at the ortho and para positions. Minus R group attached to the ortho and para position, right? As we have seen, because the electron withdrawing group, what happens? Electron withdrawing group will extract the electrons from the benzene ring, and it will convert it into a more positive character. More positive character, then easily a nucleophile can come and attack. Fine. Then you can say I can say directly proportional to minus I effect also. No. You can say also directly proportional to the electronegativity of the heteroatom of the ring. Heteroatom of the ring, that means the heterocyclic compounds. The heterocyclic compounds are of many types, like pyrrole, furan, means for a benzene ring, somewhere a 6-membered benzene ring N is attached, 6-membered benzene ring O is attached. In the first or second lecture, you can see where I have taught you everything. What do you mean by heterocyclic rings, right? No. The reaction, also one more thing, the reactivity also depends upon. The reactivity also depends upon the solvent. So it generally takes place under polar aprotic solvent. Polar aprotic solvent. It's very important. Takes place in a polar aprotic solvent. Polar aprotic solvent is very important. Important for a aromatic nucleophilic substitution reaction. Leaving group power, minus R effect or minus I effect, electronegativity of the hetero group. That means heteroatom which is attached to the ring. That means the heterocyclic compounds. Heterocyclic compounds. Right? And the is more dependent on polar aprotic solvent, not protic. Polar aprotic solvent. Aprotic solvent. Fine. Like dimethyl formamide is a polar aprotic solvent. Right? Ethers are also polar aprotic solvent. Fine. Now we'll see with few examples. We'll see some few examples. With ammonia and ethanol, it will give NH2 and NO2. That is done with NaOH. This is a polar protic solvent, and I have told you it has to be done in a polar aprotic solvent. Although it is in the reaction takes place, but it takes place at a very high temperature, 50 degrees. This takes still at a higher temperature, 200 degrees Celsius. Now the same scenario, if I take it NO2, and Cl, what will happen? Suppose if I treat it with aqueous Na2CO3, and you can say 70 to 80 degrees Celsius, because there are two electron withdrawing groups, so obviously the temperature decreases. Which, and this is this. Fine. Now suppose if the same scenario, same electron withdrawing group, take for example NO2. Here it was there in ortho and para. Take for here ortho, para, and the another ortho. Both the ortho positions. Both the ortho positions and one para. NO2, NO2, and NO2. So this will take at a much lower temperature and a much simpler reagent. In the previous scenario, it was Na2CO3. In the scenario, it was Na2CO3. Previous to that, NaOH. In presence of NaOH, it was giving OH. In presence of NaOH, it was giving OH. Here, in presence of two ortho and para positions of electron withdrawing group, it was taking Na2CO3, but at 70 to 80. Here, when both the ortho and one para position, NO2 is there, which is electron withdrawing group, then it is taking place in presence of a weaker reagent like water. That too at a room temperature, you can say 25 degrees to 27 degrees it can be. Fine. Now, now same thing I will take heterocyclic compounds. Take for example pyridine. This we will treat with NaNH2. This is NH2. Similarly, take for example, if I take it with C6H5Li, then it will give me right. Sorry, QH. That will give me OK. Now, this is a pyridine where the 6-membered ring contains nitrogen. Similarly, if there is a 6-membered ring which contains oxygen, then the reactivity pattern changes. As I have told you, the reactivity also depends upon the reactivity also depends upon the heteroatom of any compound. Heteroatom in pyridine case, it will become be nitrogen. In this aromatic ring, yeah, there is a nitrogen. Another aromatic ring, there is oxygen. Right? A furan type ring. Furan type ring. Now, the electronegativity of we know nitrogen is lesser electronegative as compared to oxygen. Right? So oxygen is more electronegative. Oxygen is more electronegative as compared to nitrogen. So this will have a more better reactivity as compared to this. Right? So oxygen will be more better reactive as compared to nitrogen, because nitrogen is more electronegative. Oxygen is more electronegative than nitrogen. I think so. Up till now we have understood it. Now I am through for the day. I think so. This much is first enough, quite enough for you to at least now go through the lecture and try to understand this. Now what will happen in the next lecture, that is lecture 15. In that I will take, now since today I have taken aromatic nucleophilic substitution reaction. Now in the another lecture, next lecture, I will take aromatic electrophilic substitution reaction. Today I have taken ARSN, right? That is aromatic nucleophilic substitution reaction. But in the next lecture 15, I will take ARSE, means aromatic electrophilic substitution reaction. And then I will take the general characteristics of it. What are the general characteristics of then different types of right? Then I'll take some few mechanisms. Simple one or two mechanisms I will take. What will be the mechanism of the after doing mechanisms, I prefer that so lecture 15 will be of will be a bit lengthy, in which now so that means I have till 15 I have finished everything, aromatic nucleophilic substitution and then aromatic electrophilic substitution, and if time permits I will go with the next type of reaction, which will be elimination aromatic electrophilic it is. Then I will take aliphatic electrophilic substitution reaction. Aliphatic electrophilic substitution reaction. Previously it was aromatic. Then it is aliphatic electrophilic substitution reaction, in which we will see some few examples. And then another type of reaction which will be elimination reaction. Elimination reaction. Then the types of elimination reaction. Right? So aromatic electrophilic substitution reaction, the general characteristics, types of ARSE, then the mechanisms, and then another is aliphatic electrophilic substitution, then different types of those, and then a few examples, and then the elimination reaction and the types of elimination reaction. Right? So I prefer that you see this lecture and correlate with the previous lecture, and so that you can easily understand the concept. So I hope you might have understood it. Just I shall meet you in the next lecture where I will be teaching you all these things. So once again, share this video with your other friends and like-minded people, who are students and people who have an interest in chemistry and who are about to give our competitive exams. Any competitive, and these are such basic thing, if you understand the basic, then for you it will be very easy for any competitive exams. Fine. So I'll meet you in the next lecture. Thank you. I shall say thanks. I'll be leaving now. Thank you. Thanks a lot. Namaskar.